We're going to talk about 3 different laws coming up here and the relationship between the variables that are associated with them. Today we're going to talk a little bit about Boyle's law here, and I think that's as far as we'll probably get today. We'll do 2 tomorrow and then one final one that kind of combines everything together, which is quite handy for us. So Boyle's law is the first one we're going to talk about here. When a sample of gas has its volume changed at a constant temperature, so the temperature is not changing, we're just changing the volume, its pressure also needs to change accordingly. Okay? As the pressure of gas results, from the frequency of collision between gas molecules with one another in the container. So remember, pressure is measured based on the collisions of gases between molecules and between the sides of the container, right? If we're not going to change the temperature, when we don't change the temperature, we're not changing the speed of the molecules, right? We're not giving them any energy. So this is really fancy here. It says no change in temperature equals no change in kinetic energy. Or, in other words, no change in temperature means that we're not speeding up the molecules or slowing them down. Okay, they're going exactly the same speed they were before. And Boyle's law states the following, and this is really what you need to know about Boyle's law right here. Okay, so you need to know this relationship between the volume and the pressure is what this relationship does for you. And you can draw a few diagrams here if you want. Don't even tell me these are not good, because they're awesome. So let's say you have 2 cylinders here, right? Boyle's law states the volume and the pressure. That's the relationship between volume and pressure. What is that relationship? And it is, well, let's take a look here. Volume is quite, in this case here, larger, and in this case here, quite a bit smaller. And simply put is, you know, when we talk about gas molecules, when we talk about pressure, we talk about the collisions between them. Well, in a larger volume, you're going to have less collisions, because there's more space between the molecules, so they're going to bump into each other less often. They're going to bump into the sides of the container less often. So therefore, the pressure is going to be low in this container here. Okay, now what is that exactly? I don't know. How low? I don't know. It depends on how many gas molecules there are, the size of the container, etc., etc. Comparatively speaking, though, let's say we decide to compress this cylinder. So we push it down here. And now we can see that the volume's kind of lower. There's not as much room anymore. So how many collisions are we going to have, comparatively speaking? We're going to have more, right? Because there's less room for those gas molecules to go. So they're going to bump into each other more often. They're going to bump into each other more often. They're going to bump into the side of the container more often. And because they bump into each other more often in the side of the container, the pressure has to, in fact, go up. Okay? And that's what Boyle's law states. It is the relationship between pressure and volume in a closed system, okay, so no gas can escape, and it's the relationship between volume and pressure. Okay? So that's the first thing you need to know about Boyle's law right there. Secondly, you're going to have to know the graph that goes with Boyle's law. So it looks something like this here. Okay? This graph can be demonstrated like so. So, pressure and volume, right? You want to pick high pressure, right? The volume's going to be kind of low, right? You don't have to draw in the blue dots stuff, I'm just showing you. And if the pressure is low, so if the pressure's down here somewhere, then the volume has to be quite high there, right? So that's a relationship between pressure and volume. I'm going to ask you probably to either draw that chart or pick one out from A, B, C, D kind of thing, so on and so on. And of course, for the one thing we have to understand is for this to be true, by the way, there's a formula that relates pressure and volume right there. P1V1 equals P2V2, or the initial pressure volume is equal to the final pressure volume. We're not going to worry about that today. We'll do that tomorrow. Okay? There's a reason. Which can be used if you can have 2 conditions are met. The temperature, remember, if we talk about Boyle's law, temperature is remaining constant. Temperature is constant. the temperature of the gas has to be constant. We could use this formula, P1V1 equals P2V2. And the system has to be closed. In other words, you can't let any of the gas escape. If you did, that's probably kind of a little bit of a problem. We're probably not going to follow these rules, obviously. Okay? And finally, we got this here, little chart. And if we have a container of gas, okay, most of the time when we look at this container of gas and we have this little plunger here, this cylinder here, the pressure on the outside is equal to the pressure on the inside. And you might even want to just start off like that. Now, let's say you put a pressure of, you don't have to write any of this down here, guys, but let's say you put a pressure of 200 kilopascals on the outside. And let's say it was 50 kilopascals on the inside here. What's going to happen? Yeah, so it's going to go down, right? So I'm pushing on here with 200 kilopascals, and it's going to keep going down. When does this plunger stop, or when does this force at 200 kilopascals, when I start pushing down, when does it actually stop? Yeah, when the two equalize out again, right? Because if you have, if you're pushing with two different forces, what happens? Well, that force, the larger one, right, pushes until basically it can't push anymore, right? It forces the other one into 200 kilopascals as well, right? The only time that this plunger is going to stop is when eventually you make this volume small enough down here, so now it's down to here, and you have enough gas packed into there that so many collisions that also equals 200, right? If this was 200 and this was 150, well, you're going to keep pushing down once again until you get to 200, right? The force on the outside has to equal the inside. They have to equal out, right? I don't know if you guys have ever done this. I talk about this all the time, and people look at me like I'm weird. But have you ever blown up a bike tire with the hand pump? No. Okay, 3 people. Great. That's great. Good for you. We have these things called bicycles, and they have tires, and you put air into them. And back in the day, we used to have these little pumps, and you used to like push down on them. You know which one I'm talking about? Yeah, I still do too. They still work, amazingly. But you push down on it, right, and you pump an air into the tire. And the thing is you can kind of relate this to this a little bit, although technically we are changing the amount of gas. But once again, it's all about the pressures equalizing out. You can pump that tire. You can, when you first start, if your tire is completely flat, if you put a new tire on and you have no air in there, you can literally stand there with one hand and pump the bike tire up. It's super duper easy. You can do like, hey, look at me, I'm showing off. And then it gets tougher because what's happening? The pressure that you're able to put in with your little hand, like your hand, is not that great, right? So you might put in like, let's say 10 psi with one hand. And then it gets a little tougher because the 10 psi is starting to equal the 10 psi in the bicycle tire. So then you got to use 2 hands, and then you start doing the dance move, right? By the way, guys, don't do this because you'll never get a dance if you do this at the dance. Trust me, I know, because I thought it doesn't work. So, but you start pumping up the tire with 2 hands, right? And you get, at first it's not too bad. It's pretty good. You get to 20 psi. Hey, look at me. 30. Yeah, it's getting a little tougher. And then you get to like 40 psi, and it gets incredibly tough. All right? That's because, once again, the 40 psi that you're able to force with the bicycle pump is probably equaling the 40 psi in the tire. Those two are becoming equalized again. How do you override it? You got to get a buddy. You got to get more force into there. So maybe you get 2 guys on the pump, and you start like that would be weird, okay? But you get like and the 2 guys pushing down at the same time, right? And you'd have to get like 50 psi, to overcome that 40. And then once you get closer to 50, once again, they're going to equal out. And it becomes really tough, right? We don't do that anymore because most of you guys have compressors, or you go to the 7-Eleven, you push it, and it's done, right? But it becomes incredibly hard, right? That's what's happening. The 2 pressures are equalizing. You have to put more pressure in to get more, you have to overcome that pressure, that resistance, right? So that's what it talks about here, although in this particular example they're saying that the amount of gas doesn't change. In my example it was. But if the temperature and the amount of gas remain constant, the external pressure increases. It's larger than the internal pressure. So if this pressure here increases, well, this is more than this pressure down here. So it starts to force the plunger down until, once again, basically the internal pressure builds up and those two pressures equalize out. So the pressure on the outside equals the pressure on the inside. Okay? It does that through a decrease in volume, of course. Okay? That is Boyle's law. Volume goes down, the pressure goes up. Okay? Why does that happen? Well, the pressure on the outside is more than the pressure on the inside until those two equalize out. Okay? And that's Boyle's law. So